Hello everyone, welcome to Sergio Prado's YouTube channel. So this week I want to talk a little bit about power management on Linux and been working on this talk about power management. I have two conferences that I'm going to attend in a few weeks. So Embedded World and embedded online conference. And I will have a talk on both conferences about power management. So I'm working on this um, material for the talk. And I decided to just provide you a kind of preview or sneak peek, let's say, on the content of the talk and actually provide you some nice and informative content on how power management is managed on Linux. So yeah, let's start. Before we talk about power management, it's important, to understand, right, what power is and what we want to really achieve here. Like we are talking about this, right? It's a mathematical thing, right? So what is power? Power is a product of current and voltage, right? So if you want to decrease power, that means you need to decrease one of those two factors, right? You want to decrease current or voltage. Of course, if one of those factors is zero, then you have zero power consumption. But that's usually not what you want, right? Because when we talk like the main challenge for power management is to try to find a balance between power consumption and performance and also user experience, right? Uh, of course, you can have a system with zero power consumption, but then that means it's powered off. And that's usually not what you want, right? So you need to find a good balance on providing some value, right? And at the same time, decreasing power consumption. Um, we can usually when we talk about techniques for power management, we can usually like separate the techniques into kind of buckets. We have idle power management techniques and active power management techniques. Um, Idle power management techniques are techniques that you're going to apply when your system is idle or part of it is idle, right? So there is nothing to be done by the CPU. You can turn the CPU off or get the CPU into a low power mode. If a device doesn't have anything to do, then you can suspend the device. So there are techniques for that. And active power management techniques, those are techniques where you are doing something, but still you want to decrease power consumption. For example, you can just scale down the CPU frequency and voltage, right? And if we look at the hardware nowadays, like they are very complex. There are lots of features built in the hardware for power management. Um, I just want to mention a few. I mean, in my talk, I won't mention everything I know, but just on top of my head, like in the hardware, you have like let's say, let's look at this equation again, right? How can you like decrease the current? You can just turn it off or suspend a few devices, and then you can decrease the amount of current consumed by a system. Um, so in modern hardware, you have this kind of feature called clock gating, where you can just disable the clock of peripheral, and then when you do that, the peripheral is will not be turned on. And that means you're gonna consume less power. Um, Another technique, another feature provided by the hardware is called DVFS. Um, that's the idea here is that you want to scale down the frequency and the voltage of the processor or maybe uh, a hardware device. then you can just configure the system to run with a low frequency and voltage, and that means lower power consumption. So there are like other features built in the hardware, um, like you have what they call a power domain. So you have a few devices in this kind of domain, and you can turn turn them off if you want. And of course, if they are not doing anything, you can just turn them off. So turning things off, suspending devices, getting devices into low power mode, getting the CPU into sleep mode, scaling down voltages and frequencies, for example, the CPU frequency. So all of these are features provided by the hardware that we can leverage at the software level. Um, and of course, here I want to show you something, right? So I have here, as you can see, development kit. So this one is from Toradex, it's a Colibri MX6 um, with the Aster board, both from Toradex. And I have a small system here that I built with Buildroot, and I'm booting the mainline kernel, not the latest version. Let me just check here which version I'm booting. So 6.8. And I just want to show you a few features from the Linux kernels in terms of power management. So let's talk first about idle power management. So one easy, like very easy way to decrease power consumption is just to suspend your system. There is this system-wide power management technique that you can use to suspend the execution of the system or get into a low power state, right? The complete system. Um, that's what happens when you go like when you are running your Linux distribution and then you go there to that menu and then you suspend the execution, right? Or when you close down your like your notebook, um, there is a small switch that we call lead switch that will automatically suspend the execution of the system. This is managed by you can manage this in user space here in this directory. You're going to see that most of the interfaces provided by the kernel for power management, they are in /sys. So /c/power, you have several files there. All of those files are abstractions, so you can leverage power management features provided by the Linux kernel. There is one file there, that is this state file. Here you can see like the system-wide power management states available. You have free, standby, man, and disk. I'm not going over all of those states. The two most important here are man and disk, or the two most commonly used. The main state is suspend to memory. So if you activate this main state, the system will suspend to memory. That means almost everything will be turned off. Only the CPU, only the memory will get into a kind of a refresh state so you don't lose content from the memory. Actually, that's not what you want, right? Um, the other one is disk. That's we usually call hibernate. So the idea, if you enable or activate this disk state, then the system will like save the contents of memory into disk and just turn off everything. And in the next deboot, you try to recover the content of the memory from disk. I'm going to show you how to activate one of those states, right? And that's very easy. Just write the name of the state to this file. So here I'm going to suspend the system to memory. And that's it. That's what happens when you suspend the execution in your Linux distribution. That's exactly what happens under the hood. Now the only problem here is that I didn't configure any kind of wake up service. So the system will sleep forever. So let me show you how wake ups work. Rebooting uh, the system. I'm gonna mount um, a file system called debugfs because this is a virtual file system provided by the Linux kernel with debug like information, and there is one file there, wake up services. Here we can see all of the configured wake up services um, that we can use. So as we can see, for example, the RTC is one wake up service. So we can use the RTC to enable, like the alarm feature from the RTC to enable the, to wake up the system, right? So let's do this. Um, if we go here to sys class RTC, RTC0, so this is the interface provided by the real-time clock subsystem. And then there we have this wake alarm file. We can use it to set up an alarm. So I'm gonna do this. Here you can do something like this, like I want alarm, let's say maybe 15 seconds. So I want to wake up after 15 seconds. Uh, let's do this, and then I'm gonna suspend. So I suspended, nothing is happening, system is suspended, but in 15 seconds, hopefully the interrupt from the alarm, here we go, woke the system. So that's how it works. If you are able to set up uh, usually a hardware device, right, to wake up your system, then you can just sleep it and then wait for events to happen, wake up, handle the event, sleep again. That's how it works. Some devices, I mean, there is this wake up. If you go to /sys, and then if you find for these wake up files, I'm gonna find it here. Let's ignore errors. So I'm searching for these wake up files, right? Inside the /sys. You can see like um, devices that are able to wake up the system that you can see if it works. Of course, it is requires some support in the hardware and also in the device driver, right? Um, for the hardware to be used as a wake up service. For example, I know that my serial port, if I go here, sys class TTY, TTY and maxi0, this is my serial console. If I go to power, I can see there is a wake up here file. Then I can enable the serial port to be a wake up service by writing enabled to this wake up file. So now my serial port, it's a wake up service. So if I get the system into a suspended state, then as soon as I have a byte received or transmitted, this is the serial port, in my case here will be received, right? The system will wake up. So I just press enter here, and then a byte was sent from my terminal program to the device, and then that woke up the system. So that's very nice, right? That's one technique that you can use to decrease power consumption, right? You can just by default get the system into a suspended state, configure a few wake up services, especially if your system is based on events and you don't want to be running the system forever if you're just waiting for events. So you can just go into a sleep state, um, and configure events from the system to wake up the system. So yeah, that's one nice feature provided by the Linux kernel. I mean, there is another feature I'm not going to show here how it works, but call it what was the name? Auto sleep. So it's a nice feature provided by the kernel. Its origins it's from the Android um, operating system. Uh, they call it wake locks. And it's nice because you can configure the system to by default and get into a suspended state. Um, so you don't have to control that in user space. The kernel will always get the system into suspended mode until we receive an event. And there is some ways like there is a locking mechanism in user space that you can use to prevent the system from getting to a suspended state. Um, Another thing that I want to show you here is the runtime power management subsystem. So um, if it's supported by the hardware and by the device driver, you can get a device into a suspended state. And that will, of course, decrease power consumption. So for example, I'm going to show you here how that works with the USB interface. So here I'm inside the USB host controller, right? And in the directory power to manage the power of the USB host controller. Here I have several files to manage the power consumed by this USB host controller. And few of them is related to this runtime power management feature. That is this one, auto suspended delay and mass, where you can configure the device to auto suspend after a few milliseconds. It's zero, that means it will automatically auto suspend when there is nothing to be done with this device. But I can just like configure, let's say I want to auto suspend after 1 second. Then there is this other file called control. It's auto. That means it will auto suspend if there is nothing to be done. So since I'm not using the USB port now, I can check the status, that's this file runtime status. We can see that it is already suspended. But if I change control to on, then now the device is active. That means it's turned on, it's consuming power. And that really doesn't make much sense, right? Because you are not using it. So that's why by default it's usually in the auto mode. As you can see, it is suspended now. And that's very nice, right? Um, let me show you how it works. So it is suspended. That means it is like in a um, suspended state, not consuming too much energy because it's not turned on. Then I can just connect. I'm gonna connect the device to the board like a USB stick, just to show you. Now the runtime status is active. That means since I need the USB port, right? Because the device is connected to it, then the device driver from the host controller automatically turned the USB controller on so we can use it. And as soon as I remove it, after that timeout that I configured it, 1 second, then it will get to suspended again. So by getting devices into a suspended state, you can also decrease power consumption. Very nice. So I showed you like the system-wide power management feature, right, to get the system into a suspended state. The runtime power management feature is also a kind of idle power management technique, right? The device is idle, you can suspend the device until you need it. Um, so both are idle power management techniques. I mentioned in the beginning that you also have the active power management technique. So that means the system is doing something, but you still want to decrease power consumption. So one of the main techniques um, for active power management is to decrease the voltage and frequency of the CPU or a hardware device if this feature is available at the hardware level. So I'm going to show you here how that works at the CPU level, right? So there is this framework in the Linux kernel called CPU Freak for manage this kind of feature. How does that work? So that means, of course, you need some support in the hardware, right? So that means the CPU that I'm using, the processor that I'm using, is coming from NXP IMX6. It has support for this. So I can scale down the CPU frequency if I want. And there is a driver in the kernel that provides this feature for me. Um, for that to work, there is a concept called operating performance point. It's a kind of a combination of voltage and frequency at which the hardware can operate. This is usually defined in the device tree for ARM. If you are working with x86, it's provided by ACPI tables. Um, so I want to show you here the device tree from IMX6 DL, just to show you the entry in the device tree. So here you can see like this is the CPU node. You have two CPUs. This device has two CPUs. And then inside the CPU node, you can see the operating points. Here you have three. That means this CPU can operate in these three frequencies with these three voltages. And inside the kernel, there is a driver that we're going to look at this and then provide an interface for you to decide at user space what kind of operating point you want to work with, right? The highest frequency, the lowest frequency, something in the middle. I'm again in the device. So how does that work in the device? Each and every CPU can be configured, right? So I'm gonna play with CPU 0, but I could also play with CPU 1. So this is those are the files provided the CPU Freak subsystem that I can use to play with the CPU frequencies and as a consequence, increase or decrease power consumption. I can look at this file, scaling available frequencies. I can see the frequencies available. Those are the same frequencies that I showed you in the device tree. I have also the governors. So that is this concept of governors. The idea here is that you want to delegate to the CPU Freak subsystem the decision on when to scale down or up the CPU frequency. For example, if you enable the performance governor, that means you're going to have always the highest frequency enabled. If you enable this power save governor, that means the system will always run at the lowest frequency. The user space is nice because if you enable the user space governor, that means you're going to have control over the CPU frequency. Then you can set the CPU frequency if you want. There is also the on-demand governor that will scale up and down automatically depending on the CPU load. Let's see what is the current governor. So the current governor is here, is scaling governor. So on demand is by default the in my system here the governor, and I can also look at the frequency with this file scaling curve frequency. I can see it's that frequency in the middle, right? Um, all right, that means since we are using this on-demand governor, that means if I increase the CPU usage, then the CPU freq subsystem will automatically increase the frequency of the CPU. Let's do this. So I'm gonna just create a run a command here that does nothing. While true do true done a few times. So now our CPU should doing a lot of things. Then we can check the current frequency. As we can see, it automatically scaled up, right, to the highest frequency because the CPU is doing lots of things now. I can kill my script, and now we can see that the frequency scaled down again. So that's how the on-demand works. You can enable, like, change the governor if you want. So for example, let's say you want performance. So now the frequency is the highest. Or you might want to say, I want to save power save. Now the frequency is the lowest. So it's up to you, like which kind of frequency you want to use. You can just um, select which governor you want to use. In case you want to define the frequency, then you can use this user space governor. Then now it's really up to you. You can look at the available frequencies, and then let's say you want the lowest, you can just write to scaling. Oh, it's not this one, it's set speed. Then you can write to this one, scaling set speed, and now you have control over CPU frequency. There is also a nice statistics about the operating points that you are using. So as you can see here, most of the time I was in the first operating point, the lowest frequency, right? And that's a good indication on the load of the system, right? Especially if you are using the on-demand governor that will automatically scale up and down the frequency. Um, all right, and there are many more features in the Linux kernel for power management. I mentioned here auto sleep to auto suspend the system. That is the CPU idle subsystem to get the CPU into an idle state if the CPU is not doing anything. There is a thermal management subsystem that is very nice. You can monitor sensors, like you can monitor the CPU temperature, and if it reaches a specific level, then you can like trigger something like a fan to decrease the temperature of the CPU. Um, there is a power supply subsystem that makes it possible to manage the battery. That's one important thing that you might want to do, especially if your device is connected to a battery, right? You want to manage the battery level and take actions in terms of power consumption, right? If the level of the battery is low, um, that is the regulator subsystem, the clock subsystem. The Linux kernel has this concept of a power-aware scheduling that the Army people are introducing because of this Army um, big little architecture. Um, There are, of course, several user space tools like this one, PowerTop. Oops. where you can manage, like monitor and manage power consumption. You can have an idea on a per process in terms of power consumption. You can look at the idle states of the CPU, frequency scaling, power consumption by hardware, and lots of different information. Um, there are other user space tools as well. And I plan to cover, I mean, everything in my talk um, that hopefully I can share with you later here in this channel. In the end, I would say power consumption is kind of a system-wide challenge and really requires a kind of holistic approach, right? Um, you have to think about the hardware design, you have to think about the kernel device drivers, um, and of course, you have to implement a polysign user space um, that matches your requirements. Because again, you're going to have to match and try to balance the trade-offs between power consumption, performance, throughput, and user experience. I'm gonna provide you the links, some links and references in the description of the video, so including the links to my talks. If you plan to go to Embedded World and want to meet and have some coffee, just let me know. So my talk would be in the first day, I guess. I have two talks there actually, one about power management and the other about SE Linux. The first one, I think it's in the first day. Yeah. And I will do also the same talk online at the Embedded Online Conference. It's a very, very nice conference. If you want to attend, I'm gonna leave you the links in the description of this video. All right, so I hope you enjoy this content, and if you want more videos like this, don't forget to click in the like button and subscribe to the channel. Feel free to leave a comment in the video with your questions if you have any. And that's it for today. I hope you had some fun. Till next time. Bye bye.